1895, in a little university laboratory in Bavaria, Professor Wilhelm Conrad Röntgen first noticed the strange effect which led to the announcement of his discovery of X-rays. And although the news was received by the public with a mixture of disbelief and apprehension, doctors immediately saw the possibilities of the mysterious new rays and began to use them. It was not until
In the early days, the newly discovered radiation was an exciting novelty, with little hint of the harm it might cause. Thomas Edison demonstrated X-rays at an exhibition in New York in 1896 and helped to make them a media miracle. Edison seems unaware of any danger as he stands bathed in the light from the X-ray lamp, although he was soon to discover that this technology wasn't entirely safe. His assistant, Clarence Daly, whose hands were often used to demonstrate the penetrating power of X-rays, was one of the earliest people to die from a radiation-induced tumour. The rays cause cancer by damaging individual body cells, like these human white blood cells that have been subjected to very high doses of radiation. Where a normal cell will progress smoothly towards a division, the irradiated ones show severe problems as they grow blobs on their surface. Within the cells, radiation can affect the chromosomes that contain the vital genetic code, and high doses can cause major deformities and breakages. The result is that the normal mechanisms of growth and reproduction no longer work properly, and the damaged chromosomes might cause the cell to die or become a cancer cell. For many years, these effects weren't really understood as scientists continued to experiment. Despite this lack of knowledge, X-rays were offered as treatments for all sorts of major and minor problems. Devices were advertised to doctors to help children with ringworm, for example. The X-rays would make the child's hair fall out and reveal the site of the infection for it to be treated with ointment. No one knows how many of these children developed cancer in later years as a result of this sort of treatment. In fact, cancer itself, in this case cancer of the cervix, was seen as a focus of X-ray treatment, since very high doses could kill off malignant cells. And faced with a tumour like this, who could fail to marvel at this transformation after X-rays? At the same time as the discovery of X-rays, scientists like Marie Curie were conducting experiments with another type of radiation, and the first radioactive materials were being investigated in the laboratory. The most well-known was the element Marie herself discovered, radium. In the light of what we now know, drinking and bathing in radioactive water seems inexcusably reckless. And the benefits of a radioactive corset are hard now to appreciate. But there seemed to be no limit in those days to the variety of products which use radioactive materials. Some of them have since been collected by the National Radiological Protection Board in a sort of mini-museum of radiation horrors.
Dr. Mora, what exactly have we got in these cases?
A series of objects which contain radium and which date from the early part of this century. And although this is a collection that has been gathered together in the United Kingdom, you could have had a similar collection in any other country. For instance, you have the sparklet siphon bulbs at this side here, and those will be used for a sparklet siphon, and instead of having scotch on the rocks or scotch and soda, you'd be drinking scotch and radioactivity.
What's that object in the corner there called an emanator?
Well, that produces radon gas, and radon is the daughter product of radium. When it decays, it forms radon gas. And that little object produces radon, and you can either breathe it, inhale it, or else you could filter it through into the bath water and have a radium bath, as they called them. And one of those was advertised in the early years of this century, and they were told that, or the customers were told, that it would be quite convenient because you could have your radium bath at home.
What about this radioactive blanket?
Well, this is a rather bizarre way of treating rheumatism. Somebody had the idea that not only could you do this by heat with a normal electric blanket, but you could also use the gamma rays of radium, and hence they impregnated this blanket.
isn't a piece of candy stuck in Junior's throat.
Up to the early 60s, a familiar sight in shoe shops had been an X-ray machine for children to wiggle their toes under. Even if the doses were very low, the view was growing that perhaps all radiation, however low, had some harmful effects. One aspect of radioactive substances that excited many people was that they could cause all sorts of things to glow in the dark, from fishing rods to buttons. So radioactive luminous paint was applied to countless articles. Unfortunately, the ladies who applied the paint often used to lick their brushes and received doses of radiation that led years later to the development of facial cancers. Indeed, Marie Curie herself was to become one of the martyrs of radiation. She died of leukemia, caused by the substances she experimented with. But the growing awareness of the dangers wasn't enough to stop the scientific research. Indeed, the first 2 or 3 decades of this century was a period of immense scientific excitement as discovery followed discovery. Many of them were made in the UK by one of the greatest pioneers in the field, Ernest Rutherford.
The next important steps in the story took place in the 1930s here in the Cavendish Laboratories in Cambridge. Rutherford was appointed professor here in 1919, and he became a sort of legendary figure as he gathered around him a group of young men who were to become among the leading physicists of their generation. Now, we can get some idea of what it was like to work around Rutherford, strangely enough, from that crocodile carved on the wall behind me. It was carved by a Russian professorial colleague of Rutherford's called Peter Kapitsa, and in Russian folklore apparently the crocodile stands for power and terror, and Rutherford must have inspired a great deal of both in colleagues and students alike.
In our laboratories today, we live in an atmosphere dim with the flying fragments of exploding atoms. And on this occasion, I wish to say a few words on the methods and ideas employed to break up atoms and to realize, if even on a small scale, the old dream of the alchemist of transmutation of one element into another.
Rutherford and his colleagues probed the structure of the atom over 30 years of detailed experiments. One of his biggest contributions to physics was the nuclear theory of the atom, the idea that the atom had a tiny but very heavy nucleus, and his notebooks show the first sketches of this idea. But how on earth could the atom be investigated? How could an invisible and intangible speck of matter be made to yield its secrets? Well, by firing particles they couldn't see, at atoms that were themselves invisible, they discovered that there was a nucleus and that it had an electrical charge. Now, they deduced this from the fact that the majority of particles fired at the atom were only slightly deflected. However, a few that headed straight for the nucleus were very strongly repelled. It was, said Rutherford, as if a 15-inch shell had been fired at a sheet of tissue paper and rebounded. So there was obviously something very special about the nucleus of the atom. In fact, it wasn't just a hard ball either. And what's more, it seemed to change the very nature of particles fired into it. News of these experiments soon spread, and an army of scientists throughout Europe tried to make sense of them. Underlying the actual experiments were some of the radical new ideas being generated by the theoretical physicists. One of them gave an early hint of the kind of power that might be locked up in the atom. It came from Albert Einstein.
It followed from the special theory of relativity that mass and energy are but different manifestations of the same thing, a somewhat unfamiliar conception for the average mind.
This simple-looking equation has always frightened people off. What it says is that any mass m has the potential to be converted into energy, E. In fact, into an immense amount of energy. Now, to find out just how much energy you could get out of 1 unit of mass, you must multiply it by a very large number indeed, c, which is the speed of light squared. It means that 1 unit of mass, the particle on the left, can be turned into a vast number of units of energy on the right. In fact, a 1 with 21 noughts after it. If only, that is, someone could find the way to make the transformation from mass into energy. But such practical aims were a long way from the thoughts of the scientists working under Rutherford at the Cavendish. They concentrated on the task of understanding the inner secrets of the atom.
In various rooms around the Cavendish, people like John Cockcroft and Ernest Wharton produced bits of apparatus that today wouldn't look out of place in a junk shop, most of them for pennies rather than pounds. Indeed, the most expensive piece of apparatus here was said to be the famous Cockcroft-Wharton accelerator. Cost around £500, was used to accelerate nuclear particles called protons, and then shielded by the very latest in radiation protection gear at the time, a sort of lead-lined tea chest. They fired the protons at atoms until they achieved what was then an immense goal. Today is something taken for granted by every schoolboy, the splitting of the atom.
It was still pure knowledge they were pursuing, as their experiments told them more about the particles that made up the nucleus.
So although the work carried out here in the 30s was very much a stepping stone towards the harnessing of nuclear power, no one here realised it at the time. Even Rutherford, for example, said in 1933, perhaps prompted by the enormous electricity bill run up by the Cockcroft-Wharton accelerator, that anyone who looks for a source of power in the transformation of atoms was talking moonshine. And it wasn't really until early 1939 when two famous papers were published in the scientific journals reporting the first verified experiments on nuclear fission that it was realised that the powerful forces locking the nucleus together could be released. So Rutherford was proved to be wrong. There was an immense source of power in the atom.
The key discovery of this period was nuclear fission. The fact that if you fired a neutron as an atom of uranium, the atom would sometimes split in a very dramatic way. When the split happened, the atom gave off 3 more neutrons and a burst of energy, gamma radiation. But since it was neutrons that started the splitting, if there were other uranium atoms around, one or more of the extra neutrons given off could now cause them to split. You would get a chain reaction. Now, if more than one of the neutrons from each fission split other atoms, the chain reaction would accelerate, releasing more energy and more neutrons each time. If the conditions were right, this chain reaction could trigger off an immense explosion. The implications of these pieces of pure science assumed a new significance with the outbreak of the Second World War. The chain reaction could form the basis of a bomb more powerful than any other. British scientists were asked to advise the government on the design of such a superbomb. Among them was Rudolf Piles.
It had been taken for granted that you could not make a weapon with natural uranium, and that indeed is true. But what we suddenly realized was that if you could separate the uranium isotopes and pull out the very rare isotope 235, then a reasonably small quantity of that could make a very effective weapon. And while isotope separation was something very difficult, which had been achieved only in minute quantities in the laboratory, it seemed worthwhile to do it for this result.
Meanwhile, the British government was losing interest in the whole idea of such a superbomb in the face of the more immediate Nazi threat. However, the scientists continued with their researches, and in the summer of 1941, a select steering group, known as the Maud Committee, presented a report on the uses of uranium for a bomb. This report was sent to America, together with a number of leading British nuclear scientists. A grant of $2 billion was made by a Congress that wasn't told it was to be spent on the ultra-high secret Manhattan Project. The world only learned of the scientists' success on August the 6th, 1945.